All right, so welcome to Math 409, problem solving. And what I want to do is a little bit different than I did the last time I taught this class. So the goal is generating functions in the Catalan numbers, but I'm first going to talk about a related problem that I did years ago with my kids when they were at a daycare in the Amherst area. And since this is being recorded, that is all I will say while it is being recorded, but happy to chat more about this later. And so we'll see later on that the Catalan numbers are defined as the number of paths from 0, 0 to NN that stay on or below the main diagonal. So just going to Wikipedia, you can easily grab the first couple of terms in the sequence, and you can also get a nice graph showing you all the different paths. I don't want you to do this. So I'm not making this an actual assignment, but I strongly urge you for class next time, try to write down a recurrence relation for the number of paths from 0, 0 to NN. It may be a more complicated relation than the Fibonacci's. And if you have that, try to solve that using generating functions. And we'll talk about generating functions at the end of the talk today. And so again, this is not meant to be an intense class that is overwhelming you and stuff. This is meant to be conversations about how to think about mathematics. And so I would much rather do less material and even related to this more basic material than to just go through warp speed advanced stuff. All right, so the official title for the talk when I give it is From M&Ms to Mathematics, or How I Learned to Answer Questions and Help My Kids Love Math. For anybody who has cultural references to Peter Sellers movies, anybody know what movie this is in homage to? Nope, not a bad guess.
Oh wait, is it something about the atomic bomb?
Yes, Dr. Strangelove. Great, great movie. All right, so I've given many versions of this talk. The first one was to math educators. So when I was speaking to high school teachers of math and science, what do we want to cover in the curriculum? A lot of things we cover now were not covered when I was a kid and vice versa. We spend a lot less time covering how to plot functions or how to adjust an integral so it matches what's in an integral table. No one uses integral tables. Now you plug it into something online. So what skills should we be teaching? The biggest thing I really want you to learn is how to attack new problems. And a lot of this is gathering data. So frequently you might be looking at the wrong problem initially, and there might be a better problem to look at to get a sense of what's going on. So ask questions, gather data. I love to use games to motivate mathematics. We'll do a lot of games throughout the semester. And then, as always, how do you implement what you've done? And depending on where you are, this could be, if you have to give a lecture, how do you discuss this in such a way to engage the audience? And that's going to be a function of who is in the audience. So this was initially done when Cameron was 4 and Kayla was 2. All right. So I don't really need to know that much mathematics for this, which is nice. This was, of course, a little bit too much for them when they were 4 and 2. You have a logarithm and the exponential function. You have x equals b to the y, then the log of x base b equals y. All right, and so we all know standard logarithms. And the biggest one that you should have a Pavlovian response anytime you see it is the log of a product is the sum of the logs. This is one of the most powerful and important properties of logarithms there is. Let me see if I do it like this for you. That seems to work better. And then we need a few basic combinatorial things which everybody should know. N factorial is the number of ways to arrange n objects when order matters. N choose k is the number of ways to choose k objects from n when order matters. Okay. And then your Pascal's triangle, the kth entry in row n is n choose k. And so you can grab lots of different pictures of Pascal online. We might have had a talk earlier in the semester where we talked about dimensionality, blacking out the odd elements. You can start to see Sierpinski's triangle emerging and start to think about, what is the dimension of this set? And you can actually get fractal dimensions. We won't need that, of course, in what we're doing today, but just nice to know. All right, so I want to describe the Eminem game. So this is one of my favorite games that I have created. So when Cam was 4, he asked the following question when I picked him and his sister up early from daycare. If you're born on the same day as someone, do you die on the same day? And this is a really good question. So how do you explain randomness to a 4-year-old? Well, one possibility is his mother is an identical twin. Look, Aunt Sarah's dead, but mommy's okay. No, okay, you can't do that. Well, you can, but there's a lot of issues if you do that. So how do you explain randomness to a 4-year-old? So I created the Eminem game. So everybody starts off with K M&Ms. We did 5, and we go 1, 2, 3, toss, and you all toss a coin. And if you get a head, you eat your M&M, and if you get a tail, you don't. And as soon as you no longer have any M&Ms, you're dead. When I was explaining this to one of the grandparents of a friend of Cam at a birthday party when he wasn't that much older, she wanted to use this. She was a children's writer in one of her stories. But she was saying, instead of people dying, could people maybe be, no, they have to be dying. So, sadly, the publication rights fell through because we were not willing to change. Kids have to learn from an early age, life is hard. If you look at this, what do you notice about the M&Ms for Kayla, Cam, and myself? Same number, good. What else? Okay, what else? Actually, no, mine has 3 colors. It's orange, green, black. There's 5 in each. What else do you notice? Think like a 2-year-old or a 4-year-old. They're lined up. How are they lined up? So vertically, but what else? Look at them. What do you notice? The kids are choosing their M&Ms. Do you notice anything about how they chose? The one on the left is Kayla, then Cam, and I got what was left. It doesn't matter for this problem, but what do you notice? Yeah, Kayla chose all the blues. Kayla wanted the blues. And she wasn't able to get 5 blues, so she took 4 blues and she took a yellow. What about Cam? What do you notice about his? Red, orange, red, orange, red. He wanted an alternating pattern. A lot of times you have things and problems that have absolutely no bearing on what you're doing. This is a great example. And when you're playing with, sure, if it makes you happy to do this, absolutely you could have all the blues. Do M&Ms taste the same? Do people want to experiment in next class? All right, so if somebody sends me a reminder, I'll bring M&Ms to the next class and we can see if you can tell a difference in taste. All right, so what are natural questions that you could ask about the game? So again, each person starts off with K M&Ms, you toss a coin at the same, each one tosses a coin at the same time. If you get a head, you eat. If you get a tail, you don't eat. As soon as you run out of M&Ms, you're dead. So what are questions you could ask? So each person has their own coin. And we'll say the coins all have the same probability of hits. So what questions might you want to ask about the game?
What's your life expectancy?
What's your life expectancy? How long do you expect before you die? What else might you expect to ask as a reasonable question? What was the original question that motivated this? Yeah, what's the probability that you die at the same time as someone else? That's what motivated this. Kim wanted to know, if I was born on the same day as someone, will I die on the same day? And so you could generalize the game. You could have more people, you could have a biased coin, but we want to calculate, how likely is a tie as a function of K? We'll concentrate on just 2 people. All right, so again, it's very important to ask questions. Once you ask questions, we have techniques to solve questions. This is why you're math majors. We have a whole collection. The hardest part in many problems is figuring out what is the problem. What should we study? Okay. So here is a plot of the probability of a tie as a function of the number of coins. So if there's 2 players and you have 2 coins, and you have 1 coin, it's a 33% chance, 2 coins, 19% chance, and so on and so on. Can you look at this and predict, well, what's going to happen in the future? I can expand it out and give you up to 110. Is it easy to look at this and tell me, where do you think it'll be at, say, 220? What could we do that might make this easier to understand? What transformation of the data? Logs. So always, always, always consider doing a log-log plot or a semi-log plot. And so it's hard to predict what comes next. If we take logarithms, we get the following. Does this look like a straight line? So I have a straight line detector, right? It's the envelope. If I put that on, that looks pretty good, but this envelope is, not big enough for what we're doing. Fortunately, I teach 2 classes and I have 2 envelopes, right? So using the double, does this look like a perfectly good straight line? Or does it look like there's some issues? Does it look like a perfect straight line? What do you notice though about the straight line or the approximation to the straight line? It gets straighter as we go further down. So maybe for small values, we haven't really hit the limiting behavior and things are fluctuating. This is a general phenomenon in life that a lot of times it takes a while for things to kick in. And then once things kick in, very different. And so here is the best fit line. How many of you have not taken a class on how to find the best fit line, how to do a linear regression? Is there anybody here who has not done this? Okay, excellent. So there's beautiful closed form expression if you use the method of least squares, if you count errors by squaring. If you count errors by absolute values, there's no closed form expression. You have to do a lot of work. This is why we use squares, because calculus and linear algebra is available. The way I like to phrase it is if I'm being hired, I use squares. If I'm hiring someone, I ask them to use absolute values. The absolute values does a little bit better job. It's not as sensitive to a few small values. Those few values in the beginning have a huge impact on the line. And so if we try to calculate the probability of a tie, we get that the probability of a tie with k M&Ms is about 0.2412 divided by k to the 0.5456 approximately. So if we want to predict what's going to happen at 220, we get 0.01274. The correct answer is 0.137. Is that a good or a bad approximation? It's not horrible. I'm getting the first 2 decimal digits right. I've got 0.127 versus 0.13. So it's off by a little bit though. Percentage-wise, however, if you look at the ratio is a decent percentage. So I am off by a decent amount. And what do you think is the cause of this? Why do you think it's not doing such a good job predicting? It's the first few points. So what could you do that would give a better prediction? Yeah, throw away the first half. So I'm going to look at basically 50 to 110. So I almost threw away the first half. So I threw away essentially the first 49 points. And now when I do that, if you have really good eyesight, I will zoom in, that is almost perfectly going through the center of the points. It's amazing how great this does. And so now the formula is a little bit different. 0.205437 divided by k to the 0.50553. And now, if I want to predict, I'm getting 0.01344 versus 0.01347. So again, my data was only up to 110, and I'm now predicting something twice as far. That's pretty good. So it is amazing how well you can often do by looking at small values and extrapolating. Of course, this is a pure math class. We are the Department of Mathematics and Statistics, but in this wing, we like to prove things. So the question is, how would we prove this? So this is one of my favorite theorems and a wonderful way of proving it. So can anybody tell me who these players are? Larry Bird and why would I choose them? Good shooters. Boston. right? And our arch rival, the Lakers. So how many people have heard the phrase beat LA? So this is one of the Boston chants. It actually started when the Boston Celtics were playing the Philadelphia 76ers. And it was clear that the Sixers were going to beat the Celtics in the Eastern Conference Finals and advance to LA. And as much as we hated the Sixers, we hated the Lakers more. And the Boston Garden just erupts. We're not saying win 76ers, we're still, on the negative side. But, huge rivalry between Larry Bird and Magic Johnson going back to their college days, I believe. And so we're going to look at a wonderful problem, which will give us a proof of the geometric series formula and a wonderful math idea. So Bird and Magic, they're playing, color code to make it easy. Bird always gets a basket with probability P, Magic with probability Q. They never tire. They always hit with the same probability. You could do P sub B and P sub M for Bird and Magic. Sometimes people like to use Q for 1 minus P. So here I'm using P and Q for Bird and Magic. So we want to calculate the probability that Bird wins. Let's call that X because we like to call things X. So we're going to break it into cases. What is the probability Bird wins on his first shot? P. What's the probability Bird wins on his second shot? So how would Bird, I'm sorry? P squared Q, not quite. P squared means he gets 2 baskets and Magic got 1 basket. Remember, the first basket wins. He misses. Misses. Right. So what would that be? 1 minus P, 1 minus Q times P. And then Bird winning on his third shot or his nth shot would be very similar. It's just miss, 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 hit. Well, let's introduce R to be 1 minus P times 1 minus Q. Whenever you use something so many times, it's good to introduce notation. So X, the probability that Bird wins, is just P plus RP, because they both miss, and then Bird gets it, plus R squared P, and so on and so on. And what's nice is these cases are mutually exclusive. Bird cannot win on his 4th and 8th basket. Once you get a basket, the game is over. So we can pull out a P, and so the probability that Bird wins is just P times the geometric series. So if you happen to know the geometric series formula, you're done. What I'm going to do is I'm actually going to use this as a way to prove the geometric series formula. So here's an alternative way of proving the geometric series formula, and it introduces one of the greatest ideas in mathematics. So let's try to calculate the probability that Bird wins. So Bird could make his first basket with probability P. Or Bird could miss and Magic could miss. So imagine we're in the world where Bird and Magic have both missed. What is the probability from this point onward that Bird wins? It's no. That's the probability Bird gets the next basket. What is the probability that Bird wins given that Bird and Magic have both missed? It's X, right? X is the probability that Bird wins when Bird starts off with the ball. Once they've both missed, it's like we've reset the game. And so from this point onward, we've just started the game over. If they both miss 1,000 times, this is the idealized Bird and Magic where they don't get tired. In real life, if they shoot 1,000 times, yes, they will be tired and the probabilities will go down. But in the idealized game, it's always P for Bird, Q for Magic. And so from this point onward, it's just going to be X. We now have a finite equation. Rather than an infinite sum, we have a finite sum. And this is a huge theme. Infinite sums are hard, finite sums are much easier. So what we can do now is we can solve X. This is just P plus RX. And so we get 1 minus R times X equals P, or X equals P over 1 minus R. But from earlier, we had that X was P times the geometric series. So now when we substitute in, we get 1 plus R squared and so on is equal to 1 over 1 minus R. We have a proof of the geometric series formula. Whenever you see a formula, you always want to ask, where is it valid? For what values of R is the geometric series formula valid? So for what values of R can I use the geometric series formula? Absolute value of r less than 1. Did I prove this for the absolute value of r less than 1? What do you think? Did I prove this? I did. What does r equal?
R is equal to 1 minus p.
Times 1 minus. So what kind of values can 1 minus p times 1 minus q take on? Can that be negative? No, it's a probability. So I've only proved it for r between 0 and 1. So now, as a nice exercise, you can deduce the geometric series formula for negative r if you know it for positive r. So as a nice exercise, try to deduce for negative r for positive r. If you've taken complex analysis, what you can do is click your heels together 3 times and say analytic continuation, and you can now get it for absolute value of r less than 1. Okay, but over here, it's not that bad to do for negative r if you just group things properly. So I'll leave that as an exercise to think about. But again, it's very easy to accidentally assume something holds in greater generality. When we were doing this argument, r was a probability. The final formula holds in much greater generality, but our argument assumed that r was 1 minus p times 1 minus q. All right, so what are the lessons from this? The first is the power of perspective. This is a memoryless process. It's extremely powerful to reduce something that was infinite to something that was finite. So we can often circumvent algebra by having a better view of what's going on. The depth of a problem is also frequently not what you expect. Putnam problems are famous for this. Putnam problems look really bad, but if you look at them just the right way, they're trivial. The problem is it's not easy to look at them just the right way. The more math you know, the more chance you have of making connections. And that's, again, one of the purposes of this class. This is not meant to be a class where you are overwhelmed with a lot of work. This is meant to be a fun class where we just explore and think and discuss. The more things you see, the more things that are just percolating there, the better chance you have later in life of making a connection. Hey, this looks like something I've seen. So to some extent, I want to hit as many topics as possible in this class. Okay, so now let's go back to the Eminem game. So the first is the following is a formula for the probability of a tie. The sum n goes from k to infinity of n minus 1 choose k minus 1, 1/2 to the n minus 1 times 1/2 times n minus 1 choose k minus 1 times 1/2 to the n minus 1 times 1/2. Can anybody tell me why this is the probability of a tie with 2 people, fair coins, and everybody starts off with k M&Ms? Oh, no. You want to see a gross equation? I'll show you my student's thesis, Jake Levinson. I believe he has the best opening of a thesis defense in the history of Williams College. I'll try to show that at some point, where it's, I think, it's either a 20 or a 40 slide equation. Yeah, this is nothing. So let's look at some terms. What do you think the 1/2 to the n minus 1 times 1/2 is? Two people, k M&Ms, fair coin. What do you think the 1/2 to the n minus 1 1/2 is coming from? Coin tosses. So if I want to have a tie with 2 people and k M&Ms, what's the fewest number of tosses I need to have a tie? Not 1. I have k M&Ms, 2 people. I'm sorry, k. So this sum, k goes from n to infinity. This is similar to the Bird-Johnson. If there's going to be a tie, let's calculate the probability there's a tie after k tosses. K plus 1 tosses, k plus 2 tosses, k plus 3 tosses. So that's where the sum is coming from. Is let's calculate what is the probability that there is a tie with n tosses. If there's a tie with n tosses, what must be true about the final nth toss for both Cam and Kayla? If the game ends after n tosses, what must be true about their final toss? What must it be? The same, and in particular, not only the same, but it must be a whichever one makes you eat. So it will be a head. Head makes 3. I mean, how could it be? That's where your mouth is. I mean, really. So that's where the 1/2s are coming from. The final toss must be a head. And then for the previous tosses, you have n-1 tosses, and each one of those is going to be 1/2. And now, in the first n-1 tosses, how many heads must you get? If your kth head is on the nth toss, how many heads must you have in the first n-1 tosses? That's right. You want to have k heads total. Your last toss is a head, k-1, and that's the n-1, choose k-1. Of your first n-1 tosses, k-1 must be a head. If anybody is interested in summing this, you need help. We can provide it. If multiple people want to do this directly, you can get you the group rate, right? You do not want to do this sum. This is an infinite sum involving products of binomial coefficients. So the question is there a better way to do this? Well, given how many slides are left and how much time is left in the talk, almost surely. So I want to try to show you a better way of doing this. Now, it does simplify. If you've ever seen hypergeometric functions, it does simplify to the special value of hypergeometric function, but there's other ways of approaching this, and that's what I want to cover. So where did this formula come from? Well, in each turn, there were 4 possibilities. Both could eat an M&M, just Cam, just Kayla, or neither. The probability of each is 1/4. Of these 4 events, which event is a little bit different than the others? Neither eat. What does this remind you of from the basketball game? Both misses. So if they both miss, it's like that never happened. So if neither one eats, it's like they never tossed. And so if you throw away that possibility, then on every turn, at least one M&M is eaten, the game is going to be finite. And so if we do that, we have our formula here, but now if we do this as a memoryless process, there's only 3 possibilities. And each one of them now has a probability of 1/3. And with a little bit more work, you could actually show that this is the formula. It's not an extremely pleasant formula, but it's a finite formula. And for a finite value of k, I can very easily plug this in and compute it. And so it's really not hard now to calculate these values. Okay, let's try to think about other ways of doing this. So why am I representing Cam's number of M&Ms by C and Kayla's by K? Yeah, first letter of their names. Choose notation that's easy to glance and look at. This is why big F is the antiderivative of little f. The worst notation I ever saw was in a physics textbook, P = mf, where P stood for force and F stood for acceleration. Horrible, horrible notation. It's not wrong, but it's not going to make it easy to follow. So by looking at CK, it's very easy for me to remember what's going on. Why do I put Cam before Kayla? Is it because I love him more? Alphabetical order, right? Have to be very careful on that one, right? So now there's only 3 possibilities. So what I can do now is I can view this as a graph. So because there's so many things, I'm only going to start off with 4 M&Ms, not 5 M&Ms. And there's 3 possibilities on each move. Each one happens 1/3 of the time. And I want to calculate what is the probability I end at 0, 0. Well, if I'm going to end at 0, 0, I had to hit 1, 1 immediately before. That's the only way. So I have to figure out what is the probability I end at 1, 1. And then once I end at 1, 1, what's the probability that I end up at 0, 0? It's 1/3, whatever that probability is. So we can break this up into stages. We start off at 4, 4. There's 3 possibilities. So I can move to 4, 3, 3, 3, or 3, 4. And then at the next level, the 4, 3, and the 3, 4 could move to 3, 3, and they could also move down. So first I have the probability flow from the 4, 3, and the 3, 4. And then I have the probability flow from the 3, 3, and I now have my probabilities. And I can just keep going. I'll have the 2 outside corners go first, then the next one, and then finally the middle one in the middle. And now I have the probability that I land at 1, 1 is going to be 33 243s. So I would just have 1/3 of that for the probability that they end in a tie. Oh, wait, I'm sorry. No, so I can't do that because I have probability at 4, 1, 3, 1, 2, 1, and so on. That probability can flow over. So all I really care about is how much of that probability could be flowing inward. So I just go through and see finally how much ends at 1, 1. It'll be 245 out of 729. And then I take 1/3 of that. And so we'll see that it's about 245 over 2187, or about 11% of the time it ends in a tie with 4 M&Ms. Okay, so there are connections of this to mathematics related to the Fibonacci numbers, which we've seen multiple times. So one of my favorite formulas, which we've seen and we'll see a proof at the end of the class today by generating functions, is Benet's formula for the Fibonacci's. So this allows you to jump to any Fibonacci number immediately. Now, let's try to look at what we have here. We have a more complicated recurrence. We have a recurrence with 2 indices. So we're going to define XCK to be the probability of a tie when Cam has C M&Ms and Kayla has K M&Ms. If both of them have 0, we'll just say that it's a tie. If C is greater than 0, then XC0 is going to be 0 because Kayla's out of M&Ms and Cam still has some. So the boundary conditions are very easy. And we get the recurrence relation XCK is 1/3 XC minus 1K minus 1 plus 1/3 XC minus 1K plus 1/3 XCK minus 1. Out of curiosity, how many people have seen recurrence relations with 2 indices? So they're a little bit more involved. There are methods to solve them. There are generalized generating functions that we can use, but bless you, but there are ways around that for problems like this. Now, of course, this was because we were smart and we saw that the case where they both had no M&Ms doesn't really matter. What if we weren't? The more natural recurrence relation involves 4 possibilities. Well, when you see this relation, what's the first thing that comes to mind that you should do? Okay, we can move the 1/4 to the other side, sure.
Yeah, can suppose the 1/4 XCK.
Yeah, there's an XCK on both sides. So move the XCK over to the left-hand side, and you'll get 3/4 XCK. And then when you multiply both sides by 4/3, now all of a sudden you have the recurrence relation from before. So if you didn't see the memoryless process, when you actually do the algebra, it actually leads you to the memoryless process, which is really nice. Okay, so we have this recurrence relation that we want to solve. We could develop the theory of solving recurrence relations in 2 indices, or if we only care about small values of C and K, we can actually do this directly. Everybody agree that x00 is 1? Well, we know x10 and x01 is 0. So now x11, we just use the recurrence relation. And so we now know x11. Now that we know x11, we can now start working on the 2's. x20 is x02 is 0. To calculate x21, we use the recurrence relation. We just need to know things where the indices are now 1s. And now that we have x21, we have x12, and now we can calculate x22. And we're done. And now we know all the 2's. And similarly, you can do the 3's and the 4's. So again, always try to do simpler cases, always try to do easier problems. Just because I tell you, hey, solve this, that doesn't mean that's what you should solve. Sometimes it's, okay, you want me to solve this, I will eventually solve that, but let me solve a simpler problem first, build some intuition, and then I will do the problem that you want. This is a great way tests have of confusing people, is they give you a general case to explore, and they don't tell you, look at the smaller values, we can actually build up some intuition. Okay, so we talked about Catalan numbers at the start of the lecture today. The Catalan numbers is the number of ways to walk from 0, 0 to NN on a grid. So you can only move east and north for the Catalan problems. This is very similar, except in addition to being able to move east and north, you can also have the northeast step, where you move 1 unit east and 1 unit north at the same time. So this is a generalization of the Catalan numbers. Okay, another way, the Catalan numbers occur in so many different areas of mathematics. One of the other applications of Catalan numbers is how many ways can you put down left parentheses and right parentheses such that as you read from left to right, you've never read more right parentheses than left. It's about number of ways to write down legally ways of combining things. All right. So what we want to do is we want to learn how to take data and extrapolate and build some intuition. So here are the probabilities of ties for k goes from 1 to 8. Does anybody notice anything about any parts of these numbers? So 1/3, 5/27, 11/81, 245, 21/87, 1921 out of 19,683, and so on. Anybody? So the denominators are powers of 3. Are they going in a strict order? So this is where, if you do too much algebra, you can actually make things painful for yourself. 11/81 might be better written as 33 over 243. Is that there was a cancellation possible with the numerator and the denominator, and the fraction was written in the lowest form. Don't write it in the lowest form. So sometimes simplification can actually be bad. And so it turns out that the denominators are 3 times 2 to the k minus 1. But what happened is we actually had a simplification possible when k equals 3. We should not have done that. So again, when you're trying to find patterns, be very careful about doing extra simplifications. Okay, so now we have numbers 1, 5, 33, 245, and so on. It turns out there's an absolutely beautiful website called the OEIS, the Online Encyclopedia of Integer Sequences. I know the creator, I've made contributions, as have my students. Basically what you do is you go online and you punch in your numbers, and it tells you any sequence it knows that starts with those numbers or has those numbers as consecutive numbers in a certain part. So if we punch these in, it's sequence A084771. And when you go online, it says a lot of things that are known about it. So the first thing, it's the number of paths from 0, 0 to n0 using steps 1, 1, 1, 0, and 1, -1. Okay, very similar to what we were talking about. Number of lattice points. Sometimes it talks about there are formulas. It actually says, yes, we actually have a generating function for it. It's 1 divided by the square root of 1 minus 10x plus 9x squared. So it's amazing how much information you can get. But it's the coefficients of 1 divided by square root of 1 minus 10x plus 9x squared. It's also the central coefficient of 1 plus 5x plus 4x squared to the n. So we saw with induction, if we know what we're trying to prove, induction is often very easy. The difficulty is figuring out what to try to prove. And so there's been several times in my career as a mathematician where I've gotten some small values, gone to the OEIS, all of a sudden, this is what I should try to prove. And now that I know what to try to prove, I was able to do it. So absolutely wonderful to know about the existence of the OEIS. All right, so some takeaways. Always ask questions. When you see a problem, always try to see, how can I push it? Are there any related questions I can ask? If you want to be a professional mathematician, if you read a paper, always ask, well, what if I remove this condition? What if I generalize to higher dimensions? How can I get something new from this? There's also more than one way to look at problems. And depending on what your skill sets are, you try, this is the principle of the hammer. You try to move the problem to something that you can do. Gather data, look at small cases. Log transforms for data is often extremely valuable in terms of just trying to get a sense of what's going on and trying to predict. All right, so what I want to do today is just quickly end with generating functions. So the idea of a generating function is to take local data, build a global object, and if you are lucky, you know things about that global object. And when you know things about that global object, you can then use that to deduce things about oftentimes the local data. So for instance, let's say we have the standard Fibonacci number. So they go 0, 1, 1, 2, 3, and so on. Each one is the sum of the previous two. So the way we form a generating function, it's the sum of fn x to the n. Now, at first you might say, I'm not really sure I can do this because I don't know the Fibonacci numbers. That's the whole reason I'm trying to study them. But you do know the Fibonacci numbers. Once I tell you 2 Fibonacci numbers and their occurrence relation, you know everything. You just don't know how to extract easily what you know. If your life depended on it and you had infinite health, will not age, wither, or die, could you calculate the millionth Fibonacci number? Yes. Pleasantly, no. But it's just simple addition. You can do it. It would just take time. So over here, we can calculate any specific Fibonacci number just by doing enough arithmetic. So how does the generating function work? We want to try to find a closed form expression for g of x. And then once we know g of x, use that to deduce things about the Fibonacci numbers. So let's look at the sum fn plus 1, xn plus 1, and goes from 2 onward. Well, I'm using the recurrence relation for the Fibonacci's. Fn plus 1 is fn plus fn minus 1. When you look at this, I have fn times x to the n plus 1. Well, if I just pull out an x, then it's going to look much nicer. So I can pull out an x, and this will become x times fn xn. For the next one, I have xn plus 2 in fn, so I'll pull out an x squared. And then for the first sum, I have fn plus 1, xn plus 1. I'm going to change my summation. I'm going to re-index. So rather than having n go from 2 to infinity and have n plus 1 as my index, I'm going to have n go from 3 to infinity and have n be my index. And similarly for the last one, I'm going to have n go from 1 rather than 2. The advantage is now everything is going to be of the form some fn times x to the n. Some of them are going to have an x or an x squared in front of it. The sums are starting at different places, so I have to put in additional terms. So for the one on the left-hand side, I'll subtract f1x and I'll subtract f2x squared. But when I put those in, that's now just g of x. Similarly over here, this is missing the x, the n equals 1 term, so I subtract off f1 of x, and the last one is fine. So I have an equation for g of x. G of x minus f1x minus f2x squared is x times g of x minus f1 of x plus x squared times g of x. Everything else is just something fixed. I can solve for g of x, and I get g of x is x divided by 1 minus x squared. We could try to expand this out using the geometric series formula. If we wanted to use the geometric series formula, what would we choose r to be? Not the root of the denominator. If I want to use the geometric series formula, I've got to write this as 1 over 1 minus r. So what would r be? X plus x squared. The problem is if you try to expand that out, x and x squared have different degrees. So when you have r squared, r cubed out of the fourth, they're going to have more and more terms. So what we want to do is basically what you were hinting at. Partial fractions. I didn't even bother asking, what is your least favorite integration technique? If you don't say partial fractions, the only reason you're not saying partial fractions is it was so traumatic you forgot about it. I have really never met anybody who did not put partial fractions as their least favorite technique. Partial fractions is actually quite useful. And here's one of the reasons why we love partial fractions. If we try to expand this using the standard geometric series formula, you should do the exercise. You'll see r squared, r cubed. They're going to have a tremendous number of terms. It's going to be a real pain. But if I factor the denominator as like 1 minus alpha x times 1 minus beta x and then expand, it's going to be much easier. And so if you do the algebra, which I strongly encourage you to do, you get 1 minus 1 plus root 5 over 2x and 1 minus negative 1 plus root 5 over 2x. And again, with partial fractions, you also get some stuff up in the numerators. You get a 1 over root 5 outside. And now I can use the geometric series formula for each of these pieces. And it's going to be really nice because it's just of the form 1 minus constant times x. And so when you expand it out, you get the following formula for the nth Fibonacci number. So this is a beautiful way to get Benet's formula from generating functions. So we start off with, we want to understand the Fibonacci numbers. We use a generating function, we bundle the information together. And so we can just write down formally the sum of fnx to the n. It's only useful because we have a closed form expression for the generating function. This is the x over 1 minus x squared. Now that we have this closed form expression, we can now use that and pull off information of the fn's. we're basically doing like a Taylor series expansion of this. X over 1 minus x squared. Modular factorials and whatnot. We're just expanding it out. We're doing a power series expansion. For the Catalan numbers, which I've asked you to do, trying to find the number of paths, you have to first find a recurrence relation. It's not going to be as easy as that for the Fibonacci numbers. And then once you have the recurrence relation, you then have to find the generating function. It's going to be more involved than the Fibonacci's generating function. And then once you have that generating function, you need to find a way to extract the information from it. So we'll talk about that later in the semester. But what I wanted to do is I wanted to just give you, here is a chance, basic electron generating functions, take local data, make global object, and then somehow extract information. It turns out for this problem, you can do this as well. It's just harder, it's more involved. And then the question is just how far can you push this? Okay, any questions on this? Yes.
Could you go back to like the generating function? Curious how we know that's when we should have to do that.
Because over here, we got g of x minus f1x minus f2x squared equals x g of x minus f1 of x plus x squared g of x.
Well, I mean at the beginning when you said it equal to the sum.
Oh, I mean, basically, it's just the object I want to understand, I just have as my coefficients. So if I want to understand the sequence an, my generating function is the sum of an x to the n. And then, of course, I don't have to do, an x to the n. There are other generating functions you can see. So if you know that I'm a number theorist, what's one of my favorite functions to study? Zeta. So the zeta function is the sum of 1 over n to the s. So there, all the coefficients are 1, and instead of x to the n, we have n to the negative s. So there's a zoo of generating functions you can look at. And depending on the problem, sometimes one form is more useful than another. If you've done probability, there's generating functions, moment generating functions, characteristic functions. There's Fourier transforms, there's Mellin transforms. They're all very similar under changes of variables, but depending on which one you're looking at, you can get very different answers. Any other questions on this? I will stop the recording here.